Hello and welcome. In this video, we will talk about floating point representation. As we saw in the other video, we did the fixed point representation where a fixed number of bits is allocated for the integer and another fixed number of bits is allocated for the fraction. And those numbers don't really change, hence the name fixed point representation. There is another way to represent non-integer values in binary, and that is the floating point operation. The common ones that you might hear about is the half, single, and double precision floating point format standards. So we'll cover the half precision and the single precision, and then I'll just mention a couple of things about the double precision, but we won't go in details into all of them, probably just the half and the single precision. Now, before we actually get started with the actual zeros and ones, let's talk a little bit about normalized representation. So what is normalized representation? Well, if you have a value in binary, let's say 1010.0001.0011. A normalized representation is basically representing this number using a one digit that is non-zero to the left of the radix point, then the mantissa, and a 2 to the power of n. So the way we normalize this number essentially is we have to have just one non-zero value to the left of the decimal point or the radix point. So here the decimal point is right here, so we have to move it 1, 2, 3, 4, 5, 6, 7. We have to put it here, so this becomes 1.01011010011. And because we moved it moved it 1, 2, 3, 4, 5, 6, 7. So this is times 2 to the power of 7. Obviously the value of the first number is equal to the value of the second number because we used a power of to modify the location of the radix point. This is kind of similar to in decimal, obviously, like if you have 935.3, you can actually write this number as 9.353 times 10 to the power of 2 or times 800. And the reason we actually need to do it this way is that with floating point representation, this one, the leading one, is going to be dropped when we store it in memory. So hence we are doing the normalization before we talk about representation. So now that's a little bit out of the way, let's take a look at the IEEE half precision floating point representation. So for half precision, basically we have 16 bits. So I'll just write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. The way those bits are used indicate different things. The most significant bit is allocated for the sign. This tells the representation whether or not the number is negative or positive. And then you have 5 bits that are used for the exponent. So 1, 2, 3, 4, 5. Those bits are for the exponent. And the remaining bit or the remaining bits are called the significand or the mantissa. So bits 0 all the way to bit number 9 are used for the mantissa or the significand. And then bit number 10 to 14 is used for the exponent. And then 1 bit for the sign, which is bit number 15, which is the sign. Hence you have 16 bits to store your values. And the power that we have here is in excess 15, meaning that the value we have in these 5 bits is 15 more than the actual number. This is one way to store negative values. If you're not sure about excess values, you can look up or review excess numbers. There's excess 15, there's excess 127, and so on. It's just another way to be able to store negative values. Let's take a look at an example. So let's say my number is 0, 0, 1, 0, 1, 1, followed by 1, 0, 0, 0, 1, 0, 1, 0, 1, 1. What I can tell from this representation, so if this number exists in memory, it's a 16-bit value. The way I can decode this one is that the first bit is the sign bit. If it's 0, that's a positive, and if it's 1, that's negative. The number is, in this case, positive, so this is a positive number. And then this is the power. This is the power that I have to multiply with when I do the 2. So this value here in decimal is 11. And then this is my manteja. And I'll talk about this in just a second. So what do I do with this one? So this is, like I said, this is a positive number. And then this is the power that I have. So it's 2 to the power of 11 minus 15, because we said that number is stored in excess 15, meaning this value that I'm looking at here is 15 more than what it's supposed to be. So I have to take 15 out of it. So this becomes 2 to the power 11 minus 15 times, I'm going to write 1 point, and I'll explain where this one came from in a second. And then I bring down my manteja. So this is 1, 0, 0, 0, 1, 0, 1, 0, 1, 1. So this becomes positive 2 to the negative 4 times 1.100, 0, 1, 0, 1, 0, 1, 1. Now I need to move the radix point. So this becomes here. So I move the radix point to the left 4 times, so it becomes 0.123, 11, 0, 0, 0, 1, 0, 1, 0, 1, 1. And now this is the number that I have, and in decimal this is approximately 0.09637. Now, where did this where did this one come from? This is actually from the normalized representation that we spoke about earlier. If you remember, before I deal with a floating point representation, I have to normalize the number before I store it into memory. And the way the system works is that it will drop the storage of this one. We don't need really to store it because we said all the numbers will be represented using normalized representation, or normalized will be normalized before we write it in IEEE format. So there's no point in storing that one. So it kind of like gets omitted before we store it into memory. So when we read the number back from memory, we kind of have to put this number back, right? We said there's that number followed by the manteja followed by the 2 times some power to the power of n. And in this case, n was negative 4, hence my number is 0.000110000, etc. Let me just take a quick side note here to give you an example of what that normalization why that number is dropped. It's kind of similar to when you say in algebra or in math, usually if you have a coefficient that's just 1, we don't write it, right? So like if you say x plus 3y equals to 0, we implicitly, or there's an implicit 1 coefficient to x. We really don't write 1x, right? That's kind of given here, so we just write x plus 3y, and we already know that x coefficient is 1. So when we write the numbers in IEEE format, like we said, we first normalize the number, and it takes a format of 1 point some manteja times 2 to the power of n, and before we store it into memory, we have this number represented this way. So there is no need really to store this value in memory, so it kind of gets dropped out when it gets stored into memory. So when we read it back from memory, we don't have to, we bring it back. We bring it back and we just pretend that it was there, and then we calculate the number based on that value. Now let's take a look at another example. So I gave you a number that was positive. Let's take a look at a number that is positive, that's negative. So I have 1, 1, 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1. And I'm telling you this number is saved in the IEEE half, it's a half precision, so it's a 16-bit value. What is the value of this number in decimal? So I want to convert this to base 10. Like I said, the first bit here is the sign bit, so technically this number is negative. And then this is the exponent. These 5 bits are for the exponent. And this value is 25, right? This is 1 plus 4 plus 1 plus 8 plus 16, that's 25. So the exponent is 25, and then this is my integer. Okay, so to write it, I'm gonna have to bring down this. This is a negative, and then it's 2 to the power of 25. I have to subtract 15 minus 25, sorry. 25 minus 15 times, I bring back this hidden one that's just going to put it out of the hat, right? And then I put my radix point, and then I bring down the integer. So this is 0, 0, 0, 0, 1, 0, 0, 1, 0, 1. So this is equal to 2 to the power of 10 times 1.2340 zeros, 1, 0, 0, 1, 0, 1. And then you can calculate this if you like. So you move this decimal point to the right, or the radix point. 1, 2, 3, 4, 5, 8, 9, 10. So this becomes 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1. This is still base 2, by the way, right? And this is equal to negative 1061 base 10. And this is how you convert from an IEEE half precision representation to base 10. So I'll repeat the steps one more time. You take a look at the bit sign. If the sign is 1, the number is negative. If the sign is 0, if the bit is 0, the sign is positive. And then the next 5 bits are the power. And you subtract 15 from that power because that number stored in memory in excess 15. There's extra 15 added to the number before it was stored into the memory, so we have to take it out. And then you bring down this hidden one, and then you bring down the integer into the number, and then you just do the math and you get your value. One thing to notice here is that for IEEE representation for this floating point, the sign immediately tells me about the number, and I don't have to do like 2's complement as we saw with fixed point representation. So in this case, if the number is, if this bit is 1, it's negative, I don't have to take the 2's complement. I just put the negative sign in front of the number. So let's take a look at an example now going the other way. So we've seen how to go from IEEE half precision to decimal. Let's go from decimal to IEEE half precision, right? So half precision. So let's say this is a D. Anyway, so let's say I have the following value, 9 point, let's say 625. I need to represent this number with the IEEE half precision floating point representation. Well, let's write the number in binary first. So first thing I need to do is convert this into binary. So 1001, that's 9 point, and we saw that 0.625 is 101. Now, so the first step is to write it in binary. The second step would be to normalize it. So to normalize this number, I have to have one non-zero digit to the left of the radix point. So in this case, this is the one I care about. So I have to move this radix point 1, 2, 3 spaces to the left. So this becomes 1.001101 times 2 to the power of 3. Okay. Now we have to calculate the exponent. So number 3, get the exponent value. We said with half precision, we store the number in excess 15, meaning the number that's going to go into the memory for the exponent is going to be 15 more than the actual number. So in this case, 15 plus 3, the exponent will be 18. And 18 in binary is 16 plus 2. So this is so this is my 5 digits for the exponent. So this is 16, this is 2, like that. And then the mantija is the remaining bits that we have here. I don't have to write it actually because you can just copy it down that way, right away. So this is 0, 0, 1, 1, 0, 1. Now I can write my number in the IEEE format. So the sign for this value, for this number, is 0 because the number is positive. So the first bit, which is the sign bit, it's positive. And then the next 5 bits are the power, 1, 2, 3, 4, 5. This is the one we calculated. So this is 1, 0, 0, 1, 0. This is the exponent. And then the mantija are the remaining bits. So like I said, there is 10 digits for the mantija. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you start with the values that you have here, bring them down. 0, 0, 1, 1, 0, 1. The remaining bits are just 0. And that's it. If that number was negative, simply instead of this 0, you will have 1 here. But it was positive in our case, so it's just a 0. And this is how you go from a decimal value into IEEE half precision representation. Okay. Now, the next precision we'll talk about is the single precision. It's kind of similar, the same exact concept, except that you have more bits. So for the half precision, we have 16 bits. For the single precision, we have 32 bits. So I'm not going to write all the fields here, but I'm just going to say there's a bunch of fields for the mantija. Then there's a bunch of fields for the exponent. And then one field for the sign. So there's 1 bit for the sign. There's 8 bits for the mantija, for the exponent, sorry. And then the remaining bits are for the mantija. So this is actually bit number 0, and this is bit number 22. So there's 23 bits for the mantija, and then bit number 23 to number 30, that's for the exponent, and then bit number 31 is for the sign. So as you can see here, from 23 to 30, there is 8 bits, and then for the sign there's 1. The mantija has 23 bits. Now the only difference between this and the half precision, like I said, is the value stored in the exponent. This will be in excess 127, right? Because we're not, we're using 8 bits, so we can store more than 15. We can go into a larger negative and positive range. In the next video, we'll do a few examples with the IEEE single precision. Thank you for watching.